Welcome to Robotics 311. This is our lecture 19. We're going to do a review today. Today we're going to talk review, which I sort of think of as a stitching together of the lectures. So I went through all the lectures, pulled out slides, and sort of tried to stitch them into one long lecture sequence that I would try to go through relatively quickly. The goal for that, I think, is to teach you, get the understanding conveyed, so that when you see questions, you know how to answer them, as opposed to kind of just learning the equations or sort of a rote style of learning. I want you to not do that. I want you to learn the material, get an understanding, and then I think you'll be able to solve the questions on the exam. And if you are looking for example questions, the quizzes and the homeworks, solution following posted, those are probably your best bet in the examples we go over in lecture. Those are your best bet for the types of questions that I ask. So I'm making all these questions like I've made all the questions for your assignments, and hopefully maybe you get a little bit of a feel for the way that I'm asking questions. They're not intended to be things you have seen a lot, but asked from a slightly different perspective, so that you have to think about it on the spot, and that's really hard. So that is a challenge, but it sort of penalizes you if you try to learn like a rote style where you're just learning the steps, because then when something changes, you have to go back to your understanding to figure out how to sort of navigate that. So that's kind of my hope, is to give you this understanding. Okay, so announcements, we have a few. T-shirts, did you guys get my announcement? I'm trying to do t-shirts, they're gonna be sweet. So fill that out and then we'll try to get them ordered. They're gonna be awesome. All homework solutions and quizzes have been posted. I think they've been updated for any of them that were incorrect. Midterm's gonna be open note. So that's the current plan. I will provide you with the notes. So it's gonna be like a deck of notes. Would you like it to be 2 slides per page or 4 slides per page? 4 slides are gonna be much smaller. 2 slides are gonna have a lot more pages. So do you guys have a preference, or how would you guys like to do this?
How small is small?
It's kind of small.
Yeah.
They're basically that big.
2.
Okay, all right, I'll do 2. So I'll probably do printed front and back and in color. Yeah.
Will they are they the lecture slides? So they will be in order of the lectures we've taken. Okay.
But they
That's
can,
how they'll be formatted.
I would plan to just print them all.
Okay.
And give them to you.
But it's not lecture 1, lecture 10, lecture they're not randomized?
No, they'll be in straight linear order. Unless you guys had a different preference, that's what they would be. Okay, so I'm gonna plan on doing 2 slides per page for everyone. I'm back, so it's gonna be a lot of pages. Okay, open note, that's good. It's gonna be multiple choice and then short answer questions. This will be paper and pencil style questions, solving something. So that's probably 4 to 5 of those, and 10 to 15 or 20 multiple choice. So this class covers a ton of material. Well, some of it is sort of technically deep, some of the analysis we've learned, and a large part of it is sort of vocabulary, concepts. Those are the kinds of things you'll see in multiple choice. The actual questions that we kind of examples over in lecture, that's the style of questions you'll see in short answer. Up to lecture 17, you'll be loud and maybe need a scientific calculator. It's the first time I've ever given an exam where that's a part of it. Normally I do everything by hand, but I think for this exam that might be helpful. It's possible that we try to add a MATLAB component. So just like we do sometimes in class with MATLAB and kind of find an answer, I might do that on this exam. Never done that before either. But that would mean that I'm giving you your laptops open during an exam, which might not be a smart idea on my part. So I would we could do it, I think, if you turn off Wi-Fi. Is that something do you guys do that in classes? Have you ever had a class with no, your exams are always no laptops. Is that right?
Or it's either no laptops or completely open.
Yeah.
Yeah.
That's usually what it is.
Open everything.
Lots
Yeah.
of open internet exams, and then they were extremely brutal.
Yeah.
Yeah.
Would it help if this was open internet?
No. don't do that.
Problems how you're planning on.
Alright, okay, that's good. So then I'll think about this. If I gave you an exam question with a MATLAB component, could I trust you to use the MATLAB part and not do other things?
The only issue with that, and I mean, I'm fine, but like, I know some students access MATLAB through Kane, and then you'll need.
That would probably be okay. Like this part of it is probably not the part that I care a ton about. It's really the cheating part. So as long as we cheated, like I would be okay with that.
That also only kind of works with that Wi-Fi because it checks licenses and stuff.
Yeah, that's true. I forgot about that. All right, yeah.
I was gonna say, if we do it like with the MATLAB portion, can then we get the notes on our laptops, like the notes that you make, so that we don't have it to like print it? I don't like using paper as much, so I just like it virtual.
Yeah,
Okay. I don't know, that was just like something also to consider, because then you can zoom in if it's really small.
yeah. I mean, that's not a bad idea, but I will probably only do that if we do a MATLAB component. Otherwise, we'll keep it closed. Yeah.
As far as the calculator goes, if I have like a TI Inspire like graphic calculator, can I use that? Or,
Yeah,
okay.
fine. So cheap.
For like the MATLAB component and like deciding on it, will you let us know like beforehand, or are we just walking in like maybe
Does it
now?
matter?
I'd have to know to charge my laptop because my
Yeah.
thing has a horrible.
I'll just charge your laptop. Just in case. I mean, if I know ahead of time with enough time to tell you, I'll tell you. Yeah.
For MATLAB, will we provide it with like a skeleton of the code, or we just gotta?
No, it would be like similar to what we do in class where I give you some things. You would have to do some MATLAB potentially, but I don't know. That's just an idea that I had. I don't know if that's really gonna work, but I kind of like that idea. Cool, any more questions? Okay, last thing is like tons and tons of resources on Canvas that are in the syllabus. My guess is people haven't looked at that too much, but they're there and they're awesome. Textbooks, websites, tutorials, everything you'd possibly want to learn background. Yep.
Alright, this is just like one last quick question
Sure.
on MATLAB. If we do a MATLAB portion, would we be able to like look up MATLAB functions like in case we don't quite remember?
Using MATLAB helps?
Yeah.
Definitely. MATLAB help would be totally fine.
Okay, cool.
Yeah.
Thanks.
Good? Okay. So now I want to like go through this set of lecture notes, and I want to do that relatively fast. There's 50 slides, 50 something. So at the same time, I want you guys to like talk with me through this. Like here, this is your time to ask questions. We can go over, we can even kind of create examples around concepts if you saw something that you wanted to see more of. But this is the time for us to learn this. So I'm just gonna start going through stuff. Stop me when you have questions. This is kind of how we started the class. It's like you start with an idea. I want to build a robot. How does that actually happen? How do you go from an idea to a machine that does what you want it to? And that starts usually with a task. You have something that you want a robot to do. And so we kind of learned a whole framework around this where you start out with, I want to build a robot. I have an idea for what it's supposed to do. It could track a position, track force, act like a virtual spring or damper, can do these sorts of tasks very easily. What we're sort of not doing is really high level computation and control. So like no localization and mapping, no navigation or path planning. We're not doing anything like that. This is a lower level version of robotics. That's kind of like I'd say mid to low level, the robot that we're building and the tools you're learning. Other tools in the robotics curriculum will teach you the higher level control and applications, but that's not the focus of this class. Does that make sense? Cool. So this is our design framework that we learned. Start out with your idea, the application requirements. We learned about speccing. There's a transmission ratio that's to be chosen. It's going to have a ratio and an efficiency. We looked at brushed motors and determining their currents and voltages. So the torque and speed is the input in this analysis, current and voltage is the output. We take that current and voltage and use it to find the temperature. Kind of learn that entire flow chart. So this all happens, called speccing. This all happens up front. It's like the first thing that you do. So what do we need? Description of the task. That's going to look like torque speed or force displacement relationships, something like some sort of understanding of what the motion and effort being provided by your robot is. And then any like secondary electrical requirements. You're going to hook it up to a battery. That battery has a voltage. So once, we can't use more than the battery supply voltage. That's a constraint. Same thing with your current limits. Where might the current limits come from? What sets current limits? Yeah.
Be the resistance in the circuit or whatever.
Yeah, so the current limits come from the heat that's generated from the resistance, and that could be both a motor side, motor could get too hot, but also the drivers will have their own limitations. So you might have constraints, you're gonna have constraints around temperature, but also around the driver. Anybody know what our drivers can take? There's two ratings that would typically be provided, a peak rating and a continuous rating. Peak would be defined for some time interval, some short time interval. Continuous is forever. I think I can do like 2 amps continuous or something like that. So as long as we're under that, we're okay for our drivers. Okay, so then we were kind of doing this analysis. This is like, how do we pick between these? So this is the kind of stuff you'll have to know and solve on the exam. So these equations describe the fundamental relationships that couple the electrical world and the mechanical world for electric motors. It's how we go from torque and speed to current and voltage. Where did this come from? That equation. The second law. That guy? Kirchhoff's voltage law. So that's where these equations come from. You'll need to know what they are and how to manipulate them. First, we typically have a description of the task. So that will come with some understanding of velocity. So we're going to solve this equation first for current, numerically take its derivative, and use it to find the voltage. One thing that you can do to help yourself prepare would be go through the equations and think, what are the variables? If you have an understanding of what the variables are, what their units are, where they come from, that's a good sign. Like that's the kind of information you would need to sort of back out what you're being asked in a question. So like, what is this? Yeah, that's the inertia of the motor that's spinning. And like, where would you get that information?
Data
Data sheet. So like that's same thing with, this is the viscous loss, data sheet. What is the difference between the motor's torque and the output torque? So if you were asked a question, like what's the difference between the torque that's coming out of the actuator and then the motor's torque that it's providing? Yeah.
Well, the motor has to like fight other torques from, for example, like the viscous loss and like the inertia stuff. So you have to essentially like take those factors in mind when choosing your motor torque because it's going to affect the output torque.
Yes. So like the motor has to produce this, the output torque, but it also has to do other things. It has to accelerate its own inertia by the viscous loss. So the motor's torque that it's producing from current is more or less than the output torque.
But it could be less, like if it took like negative effort to like fight the viscous loss and
Perpetual motion.
and inertia.
No, I'm thinking like if there's a condition where the velocity is in a different direction, it's possible that never occurs. Yeah.
Will those equations also be like part of the slides?
Yes. All the slides. You'll get them all. That's my current plan, except for the lab slides. So what I'll do is so the way we typically do slides, you guys probably know this, is like the first 15 or 10 slides is a review of the previous lecture. I'm gonna strip all those out. So then it's just gonna be lecture, 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 lecture. Cool. It'll be shorter, and I'll probably remove the lab stuff. The ballbot specific lab stuff, like navigating the command line and setting up that kind of thing. So I'll probably remove that, yeah.
How much of like lab content or like I guess things like especially like with lately what we've been doing with like the Python stuff, will that be on the midterm?
No, I mean nothing after lecture 17 for sure. And then also like this exam is not meant to really test you on the lab side of the class. The final, which is actually like the ballbot project, that's sort of meant to be grading that, or assessing that. So this is mostly focusing on the in-class content. So if you know the stuff for the labs, will help you with the class content. Okay, so we talked about transmissions, modeling them with their efficiency. This was an example of how transmissions change torque and speed. Someone talk me through this graph. What is this saying? What are these triangles?
torque is just kind of inversely related to the output angular velocity.
Yeah, so like, what this is saying is, if we have a task, that task might look like some profile in this side of this triangle. We could represent a task as torque and speed, right? So we could talk about anything, the ballbot's motion fit inside this plot and be in some region. So this is saying there's a region here of like some task. The input, that region is going very fast. When we put it through a transmission, it goes much slower, but its torque is amplified. So the same kind of task that took up this area of the torque speed curve on the input takes up this area on the output. That's the idea. And that's saying like we're scaling it by about 4 to 1. Cool? Everybody not understand that? Okay. Kind of learned like how to model a ballbot. Why did we start talking? Why did we start talking about the ballbot here? So we were learning about how to pick motors. We were learning about how to set up this pipeline, and then we started talking about the ballbot and specifically its mechanics. Why were we doing that? Yeah.
So that we know how much force we expect our motors to need to use.
Yes, how much, I would say torque and speed or current and voltage. It helps us answer that question. So we needed to get some description of the mechanics of the ballbot to do this pipeline. So we started talking about the ballbot and its setup a little earlier, and then we created some expected motion profile. And this would be part of, like when you're designing a robot, you have a task you want it to do, you might be given some information about that task, sort of its requirements, velocity, or acceleration, or you might have to make that up. And that's what we did. We kind of made an educated guess based on what we want the system to do. Well, we want it to go about 1 meter per second. We want that to take a certain amount of time, so we have some velocity here, constant acceleration, and then we map this into current voltage. Yeah.
I actually have a question about one of the other slides with the torque and speed. There. So I guess I'm still, I'm not confused about it, but I kind of want to understand better, or why do we tend to want lower speed, higher torque on the output versus the input?
Yeah, good question. The reason for that is most power, the kind of capacity to do work, comes from machine elements, usually in the form of speed. So motors can run really fast. We build things that can usually rotate more quickly than they can provide effort. That's just kind of the nature of the electromechanics and geometry of motors, so they run really fast. Same thing with IC engines. Mm-hmm. So generally, that's one part of it. The other part of it is the world we live in. To navigate this world has sort of some general requirements on torque and speed. Things have a certain size and mass kind of in the world. So if you're working with things in the world, that usually means you're working at a lower speed, higher torque regime.
Just because we can't handle the higher speed aspect of it, or it's just things don't go that fast, or?
Yeah, and they need more torque. So we have to trade them this way in order to get the effort we need, and then we don't need that much velocity or flow. So it's kind of just a artifact, I think, of the way mostly motors and engines work. They just move very quickly. If in fact, we try to build an engine or an electric motor that has the torque capacity of a human body, it would be very big, going like this. But then that would move slow and have a lot of torque.
Gotcha.
But that's kind of impractical based on its size. So it's kind of like that. Anything else? Okay. So we were inventing a motion profile that contained some of our expectations for the robot. They're encoded in this motion profile, and we use this to extract the current and voltage. So who made that profile? We did. What happened, what was going on here? What's the blue going on? Why did it go from blue to red? Yeah.
because the derivative at those points is technically impossible.
Yeah, so like this is easy to code in MATLAB, but not realistic physically, because it has sharp corners which require infinite acceleration. So I smoothed it with the MATLAB function and it gave us this. The way it did smoothing was at a moving average window, which gave us a blips in the next plot. This is also like real important. Acceleration proportional to torque, proportional current in general, velocity proportional to voltage in general. This was just modeling the ballbot, so we were getting our equations. We really wanted this equation to get the torque. And this slide basically explains the full process. So like getting our equations for the mechanics, finding our constraints, solving for motor current, solving for motor voltage, given our velocity profile. So that's kind of the whole pipeline kind of on one slide. Make sense? You're gonna have to do something like this for sure. So I won't, hopefully won't have the mechanical modeling be so challenging that this isn't a test on mechanical modeling, but there will be some modeling. It will definitely be something that looks like this. And this is what we ended up getting. So the output of this looks like current and voltage. And then we can use our understanding of physics to sort of check this. And it looks correct to me, which means we see like a large torque or current when we're accelerating the inertia. And then we end up with a low current that's just fighting the viscous loss once it reaches constant velocity. So like the more you know, if you can kind of put this information together and really understand it, you can kind of look at these kinds of shapes and know whether they're either like in the direction of correct or not. Okay, this is an example like we did in class. Yeah.
I was just wondering if you could quickly go over the constraints and how you get those.
These constraints?
Mm-hmm. Like the two of them.
Yeah, here.
Mm-hmm.
These constraints come from the no-slip condition, essentially the no-slip condition on both interfaces. So one is a no-slip condition on the bottom of the ground, and the other is a no-slip condition on the wheel to the ball. And then if you in the notes, I think I may have deleted the derivation of it, but this actually gets derived later.
Okay.
We derived that in lecture 15 or so.
Mm-hmm.
Cool. This is an example question. We solved this in class, but this would be the kind of thing, present you with a little robot challenge. You have to kind of do the analysis to tell us something like current and voltage. Cool. Any questions on this problem? Could you guys solve this problem? Again. I mean, this thing involves MATLAB, but could you analyze this machine and get equations for motor torque and speed, current and voltage? I'm saying mostly nods, which is a good sign. This is probably harder than what I would ask you, I think. Yeah.
Would the B term be provided and everything like that, the viscous loss and all of that, or?
Everything would be provided, unless it's meant to stay in variable form.
Gotcha.
Which is possible, yep.
So when we add the transmission ratio, because I remember on the homework that was something that was kind of confusing for me. There was a similar problem. So essentially, I think was how you explained it is that any term that's in regards to the output is you always have to multiply by n, and then I guess.
So maybe your question why is this divided by n and not divided by n squared? Or something along those lines?
Yeah, something along that.
So the n squared comes from things that have relationships with both torque and speed. So a spring has a relationship with torque and it related to motion. So the transmission ratio affects both of those, you get n squared. This is just torque. This is just a torque on the output, we're gonna divide that by n. But if that torque was somehow related to the motion some way, I mean, it is here, but that variable already stays, that other n comes from moving from the input to the output. And so this is already on the output, so there's no n there.
But then also why is So sometimes it's like the one of the terms is multiplied by n, but then like the other term is divided by n. I see like
Where?
the like the
This?
b, yeah. I see the substitution, but
Yep.
so I don't know.
This sets it up with respect to phi. So the answer is wanted in theta. So it sets it up with phi and then transitions to theta.
Okay, and then wait, what is so phi is that then the motor like?
Yeah, phi is the motor's motion.
Okay, so then it just okay, that makes sense.
Can you remind me what the like MLA squared over, I don't remember what that term is, and then n squared, like what, cause like
What's going
the,
on here?
yeah,
This is the inertia of the output. So this is the inertia of the motor.
Yeah.
This is the inertia of the output. So this is the inertia of a point mass on an arm.
okay,
ML squared. And then divided by 8n squared.
gotcha, okay.
If we also have dampening on the output, would we also divide that by the efficiency?
If you had a damper on the output,
Yeah.
yeah, you would divide that by the efficiency. Yeah. And then you would also divide by n squared. Yep. Good? Is that a question?
No, never mind.
Okay, now we move to thermal modeling. So we kind of set up this entire like flow chart of kind of how we do this process. We spent some time learning how to model things. We spent some time learning on operating on the electromechanical equations. And then we had to do the kind of last part of the speccing process, which is predicting how hot something gets. We learned kind of really 3 types of thermal concepts that fit generally into conduction and convection. And then we learned about thermal mass. What was great about these, we're not gonna spend too much time on it, but what was great about them is they have the same governing equations, which is essentially like Ohm's law. So this is saying, is it clear that this is basically a resistor? Heat's gonna flow through it. Okay. I can try to explain this many ways, but hopefully I think you guys are getting it. So this is just a thermal resistance through conduction, heat flowing. How about in our system, where's the conduction happening? Yeah. From the motor windings flowing to the motor housing, that's right, that's conduction. Okay, we can also talk about convection, same concept, actually like different concept, same equations. So this is heat flowing into the atmosphere, that's causing heat to rise, cool air coming in. Also a resistor, sigma was temperature in all of these notations, sigma is temperature. So we're just gonna set this up like Ohm's law, and we can change it with heat sinks, which is pretty cool. The last thing we learned was thermal capacitance. This is like energy being stored in a mass, heat energy. And we set up a little like, looks like this. This is a current source. So this would be an electrical current source. What would this, what's the like thermal analog of this?
Battery.
This would be, like, this is essentially the heat flowing. Q is the current here, is the heat flux that's coming from I squared R. So this is I squared R. It's a current source. So this would be like a fixed current through a motor. Well, I'm gonna say that's a thermal current source. It's gonna charge this capacitor, so it's gonna store energy, heat energy in the mass. And then the temperature would just be basically the temperature or the voltage drop across that capacitor. This is the kind of thing you're gonna have to know / solve. Probably more like this. See, it's possible that I try to ask something that involves the capacitors, but those are pretty hard to do in a short amount of time. So the steady state version of this, when you heat the system up, Q flowing through the system, windings are active. What's gonna happen to these capacitors?
Charge.
They're gonna charge, and then they're gonna become an open circuit. So once they're charged, they becomes an open circuit. Now we're only dealing with the resistances. So that's what this is showing, and it's saying That Q has to be essentially V over R, which has to equal V over R. So there's one thermal current going through both of those resistors. You can set it up just like an electrical problem. What is this?
The housing.
Temperature of the housing, yes. This is what?
Ambient.
Ambient air temperature. What's that?
One temperature.
Finding temp. What was the significance of this set to 0? What does that do?
You're setting the reference point as the temperature outside.
So then how do you interpret sigma W
If it's positive, it'd be temperature hotter than
ambient?
Yeah.
Yes. Yeah, that is correct. Good. Okay, so this is kind of like where we started to end the kind of specking part. Now we did these are the things that you need. You need to get transmission ratio and efficiency. You need motor parameters, thermal properties, and then you're going to choose the motor, transmission ratio, and maximum voltage or current. That's kind of what you choose as the robot builder. Cool? Then we started to learn like how to actually make stuff, which was fun. I thought that was like a really neat, I've never taught anything like that before. I thought that was pretty cool. We learned a few different types of manufacturing. We did specking, we were on physical design, so layout and manufacturing. We talked about 3 different types, really focusing on subtractive and additive. The first thing we learned was 3D printing FDM, fused deposition modeling. That's essentially like squeezing plastic out of a tube and then print something. You guys built a lot of stuff with that, which was cool. See if there's anything that I feel like I have to say to you here. Okay. This is materials, which all I kind of really want you to know for materials is essentially this information, which is like a rough understanding of what you would select for a given application. So not, I don't think you don't need to know things like the modulus or yield strength of these materials, things like that, I don't think we're really gonna worry about. Cool? We did mostly ABS, PLA, and nylon here. Stereolithography, SLA, awesome 3D printing concept. Photoactive resin is cured with a laser and it drops the support. These are really neat. Who built their parts out of this? Anybody? Somebody did, yeah, you guys? Yeah, those are really cool looking, I think. Nice looking parts. What we have in the makerspace are these Form 3 machines. So this is the kind of stuff that would probably be like multiple choice. Because there's not really like a ton of paper and pencil style questions that we can ask about this. Polyjet printers are a different type of printer that I think we have at Michigan but isn't in the makerspace. What was like especially different about the Polyjet printers? Yeah.
Multiple materials.
Yeah, I can do specifically like rubbery and soft materials, which is pretty cool. We've had the 2 places I worked before this, those in my lab. They were cool. They're really neat. They print really, really nice parts, but they get brittle over time. They're cured with UV light. Yeah.
Are they faster, like much faster or slower?
No, I think they're like about the same. They might be faster than FDM because they do like multiple areas at one time, like a printer. But whenever I've printed a decent amount of parts of these, I've never thought to myself, this is fast.
Because like I guess if you're doing like let's say like 4 parts at one time, because it couldn't just spray all at once instead of having to move the nozzle.
Yeah.
So that time for that would be faster.
Right.
Okay.
It might be. I think it might be, but I don't really remember it being much faster.
Okay.
It's possible that I think its motion is much slower.
Gotcha.
Laser cutters, these are really neat. You guys use these a lot, I think. The main thing to know, I think, is like the concept of kerf. That played a big role in what we were doing. There are kind of 3 different types of lasers. We are basically only using this kind. You guys all use that, which is pretty cool. Oop, my pencil is dying. You guys all used those in the creation of your ballbot designs, which was awesome. Water jet cutter, it has some really, really like useful properties. What is its like most important benefit?
It's cold.
It's cold. Yeah, I would say like maybe there are two most important benefits. One are, what is it's cold? It doesn't heat the material up. What's the other?
They're really thick material.
Cut through really thick material. So those two concepts make it especially useful in certain applications. Giant metal parts. But we use water jets a lot. I like them. Okay, so this was kind of like, we learned how to spec, we learned how to create the files and model things to some degree in SolidWorks. And we learned how to execute on the different rapid prototyping tools, laser cutter, 3D printers, etc. And then we kind of transitioned into like, okay, we've done manufacturing, speccing, modeling, but we didn't really talk about like layout, like how to structure, once you know your motor, your transmission ratio, your supply voltage, all your different concepts, how do you package that in a machine to do what you want it to do? And that's incredibly application specific. So it's really hard to talk about that very generally, but I'm trying to a certain extent. And then also you see a specific example of that in the ballbot. What we're doing in the ballbots, how we picked all the dimensions and spaced everything out. So this really depends on what I'm building. I kind of like set this up under the idea of like understanding motion. That was, I think, kind of the key way to explain like understanding layout, is to understand how motion goes from one place to another. And then we brought up a few different transmission types. Gearing, belt drives, which we didn't talk about, screws and linkages. These are kind of the general gearing examples. Spur gears, bevel gears, and worm gears. What is the benefit of a worm gear? Yeah.
I want to say like angular to linear motion or something along those lines.
It's still angular to angular. Because this is a screw rotating, this is a wheel gear rotating. Yeah.
You can change the plane that it's rotating along.
Yeah, I think that can be helpful for sure.
But also like it's high ratio.
High ratio, and then I think sort of non-back drivable can be an advantage. In certain cases, you might want a transmission that cannot be back driven. And worm gears are often non-back drivable, not always, but often. Yeah.
I'm still confused by non-back drivable. Does that mean you can't reverse the motor? So like, it can never go backwards?
It's not that it can't go backwards, is that power cannot be negative. You cannot drive it from the output.
Okay, but like the motor can be flipped and make it go backwards
The
though.
motor can spin in any direction.
Okay.
Yeah, this is just whether you can take it from the output and move the input.
Gotcha, okay.
If you can't backdrive something, you cannot, for example, recoup or regenerate negative electrical power. That doesn't happen. Bevel gears basically just turn your shaft 90 degrees, and then spur gears are your standard gearing. Did you guys see, sometimes in this class I showed pictures that had like helical cut gears? Anybody know anything about those? Instead of them being straight like this, these teeth are like cut at a kind of an angle. Who would know what that's useful for? It's just quieter, I think, and more efficient. Yeah.
Oh, okay.
We talked about gearing, these are kind of the main equations that define gear ratio from two spur gears, the relationships between their diameters, their number of teeth, their velocity, their torque. I put efficiency in there, just so you guys see that it's still part of it. But you wouldn't actually, this probably wouldn't be a part of N, but it would affect the torque. Pinion is a small gear. The gear is the large gear. We learned about screws, very, very useful, really common in robotics. This is a rotary to linear motion transformation. You guys had a quiz that included a screw question. I think basically no one got that right, or like that, I don't think anybody really did well on that quiz. That was kind of a harder problem. That quiz question is very similar to the, I think, difficulty level and conceptual evaluation that you might see on the exam. So take a look at that quiz. Do you guys remember that quiz? I can't remember exactly how people did, but a lot of people didn't get it. So these are the two equations that kind of describe lead screw or ball screw usage. The equation for torque that maps torque from the input to the force provided on the nut, and then the velocity relationship. What's the kind of difference between these? How does it work? Yeah.
One has like sliding contact and the other one's rolling contact.
Yeah, so in a ball screw, you can see that the screw itself is circular. So the balls are kind of rolling in that track. So it does rolling contact instead of sliding contact. They're loud. The balls rolling around are loud, but they're very, very efficient. I brought one in here, but I brought in a lead screw one time. You guys got to play with that. And that one was actually really efficient for a lead screw. You could hold it and it would drop the screw down and spin it. Cool, good. Now those equations. Linkages. I didn't put a ton of slides in here on linkages, but you will need to know them because there's tons of relationships on linkages. So here's why, or like here's something I was talking with somebody in my office hours about, like I can't remember, but I wanted to mention it. So like we didn't learn like here's how you design a linkage, right? You guys agree with that? That's not how the lecture went. The lecture really went, here's a bunch of relationships about linkages. And the reason for that is linkages, designing of linkages can come in so many different forms. It depends on what you have and what you need. So like in one version of this, of solving a linkage, would be an input and output link. You know your inputs and output links, then you're solving for the dimensions of all the other links. And once you have the dimensions of all the other links, you can move the system through a range of motion, use the kinematic links that you got before to make sure that they don't change length or separate, and that would allow you to solve, for example, a question like you saw in the homework. But that's just one way to design a linkage if you happen to have those concepts, the input and output links and locations. Does that make sense? So like there's so many different ways to design a linkage. We can't really talk about it like that. So instead you learned a bunch of relationships and hopefully you implemented them on the homework and they became more clear to you. Is there anything you guys want to talk about linkages? There's a good chance you'll have a linkage question on them. Yeah.
Just like in that image where it's described as a parallelogram 4-bar, like that doesn't say anything about like the links need to be parallel or like equal lengths or anything.
No, a parallelogram 4-bar is just a 4-bar linkage where this is grounded and these rotate. That's it. Yeah, it's just a linkage that looks like this or like this. But linkages can take on a gazillion forms. So that's one specific type that's called a parallelogram, even though it's not. It's only a parallelogram if the ratio is 1, then it is a parallelogram. Other questions? Yeah.
Will we be given like the equations for the linkages too?
All the slides. You get all the slides. So you get all the relationships. But a lot of those relationships would be very difficult to run without a MATLAB. So that's part of it. Yeah.
For gear ratio, like for the center of rotation, for the input, is it like the one at the origin? And then for the output, is the center of rotation B?
This link is rotating about this. This link is rotating about that. This is ground.
Okay, because if that were the case, would that make the gear ratio positive? Because in your range of like when you would rotate it, they would move in the same direction?
This I think would be positive and then negative, this ratio. Like as it is right now, it would be positive, but it's gonna flip. Like if I keep sending this one around, this one's gonna do this. So it'll change ratio.
Would it still be valid if you were to say that B was your center of rotation?
B is the center of rotation of what?
Of your output linkage. Like if you were to define your gear ratio as that way.
I mean, since this link isn't moving, this has to rotate about there. So this, we could define something called instantaneous center of rotation that describes the relationship between the rotation of these two links, but we didn't talk about that. But that would be if you follow this down and that down, they're instantaneously rotating about a point down there. But that's something, is that, I think, are you talking about that or are you talking about something else?
I'm just thinking of like if you were to define like the positive versus negative of like the gear ratio, like if you were to think about it moving like from, if the rotation was from C, then it would like if you were to move it to the right, then the gear, it would be moving in the negative direction, but if you move it from like B, moving it to the right, it would be moving in the positive.
This will like make a singularity. So if we rotate this over, it's gonna make a singularity. Or at least, let's see. It's hard to imagine. It's hard to imagine.
Yeah, I think it's fine.
But this link is rotating about here. This link is rotating about there. We're talking about their instantaneous rotation with respect to each other. That's where they intersect on the bottom. So yeah, learn, like check your link, like understand linkages, but also kind of know that it'll be hard for me to, if you look at the linkage equation, it's gonna be hard for me to ask a complicated linkage question because they do get intense. Okay, so we learned about compound transmissions. This is where you stack transmissions against each other. That's really common. The important part was this. I multiply the transmission ratios and we multiply the efficiencies. Yeah.
And the diametral pitch for these types are normally the same for like gears in a compound transmission.
I think generally they are, but there's nothing that says they have to be.
Okay. Like for the homework question.
They were.
Okay.
Yeah, they had to be to answer that question, unless I gave you the diametral pitch of the second set. But I think there's nothing that says they have to be, but they almost always are. I think, right?
So like on the midterm, unless it's stated that it's not, we should just assume that it is.
Yeah, I think that seems fair. Okay. So we did transmission. How do we create motion and move it from place to place? How do we have that motion provide a ratio that we care about? And then we tried to talk about, well, how does that motion actually fit into this project, this ballbot? So we started learning like the mechanics of the ballbot in more detail. We learned these relationships, contact points, locations of torque, alpha, the kind of angle that the wheels make contact on the ball. We learned beta, we'll talk about that more in a second. So we kind of began to understand its geometry, which is very important. If I hadn't given you this, you guys would have thought, oh, I need to have this, and you guys probably would have started making it. Like if I said, design a motor mount, and I didn't give you like the planes and such, you guys would have been like, okay, what do I need to know to do that? You would have gone back and created this. So since we gave you that plane, we kind of skipped all this, but we wanted to show it to you. This is all information that you would need whenever you're designing a robot. It's kind of like really understanding its geometry. This is where we started to introduce the planes. The two planes we're going to control motion in, the XZ and YZ planes, and then the XY plane that we can look at from the top. We did some mapping of torque in that plane. This is also like something you're going to have to know. So in terms of like ballbot stuff, anything that looks like this, lecture content, that's definitely, consider that to be like high priority for the exam, not to be confused with ballbot stuff in the lab. So for the homework, which plane are you guys creating motion in? The XY plane? You're spinning it about the vertical axis in the XY plane, yeah? Cool. So if we want to balance and drive, do we need the XY plane? No. But we might use it. I think this other idea, as we get into the steering control, this idea of having it rotate using kind of the controller and then drive forward. So that would be its only motions, rotating and driving forward. So then to drive it, you steer it. You know, that's one way to do it. Another way would be to actually try to have it move in all directions without rotating. But we'll get to that. Torques and motion from the virtual wheels is not the same as the real wheels. This is how we got our equations to convert torque. Conservation of torque across the system, so the torques from the imaginary planar wheels, the real wheels. We solve for those equations of torque, and that we could derive from like the rest of the equations that were provided. You should know this picture well. Like, what is this picture describing? Somebody talk me through this picture. Somebody who hasn't talked much or answered much. If you haven't answered much today, can you help me with this picture? Any volunteers? You've helped me already. Somebody who hasn't talked. Yeah.
It's the position of the wheels on the ball, and then the direction of their torques and forces.
That's right. So what is this dashed line?
That's the ball diameter circumference. Yeah.
Yep. That's right. And so what is this?
That's the circle that the wheels are gonna roll on the ball.
That's right. So that's the contact circle. It's at RK sine alpha. That's RK. These are the torques and forces from the actual wheels. Yes. Awesome. You're gonna need to know that. This was the equations from the dissertation. Just provides it in a little bit more general form, in case that's helpful. What's beta? Somebody who hasn't like talked much. Talk me through beta.
I forget.
What is beta? You know what beta is. Do you know what beta is? Do you remember this? Okay, beta, if we go back to this picture, something has to orient T1, T2, and T3 with the X and Y axes. There needs to be some orientation. We have to make a decision there. We decided to align motor 1 with the y-axis. Beta is the angle to motor 1. For our case, it's 90 degrees. So what we did here, this is the general form, and all the equations that you're provided, we've already accounted for beta, so that's why you don't really see it ever. But if you wanted to change that for some reason, you could. Okay, I think we're doing good on time. We have like 20 minutes. And I'm 41 of 53. You're doing great. Then we learned data acquisition, kind of sensing, data acquisition, mechatronics. Yeah.
I have a question going back to the torque stuff. There's one equation that relates the virtual to the real torques. T1 plus T2 plus T3 equals Tx plus Ty plus Tz. Is that literal? Like if you add up the values of each, they should add up? So
Yeah.
Alright.
That's conservation of torque.
Okay.
Yeah. Those would be like the vector forms, but yes. Yep. So we started talking about data acquisition, sensing and mechatronics. So up to this point, we've done how do you spec a robot? Like how do you choose its characteristics? How do you choose its physical layout and transmission components? And how do you make it? How do you manufacture it? And now we're beginning to talk about like how do you actually interact with it? And that's kind of where this is going. Data acquisition, sensing, mechatronics, control. This was data acquisition of a analog sensor. what's an analog sensor provide? Excuse me, provide, yeah. A continuous voltage. It operates a continuous voltage that represents, it's gonna be proportional to some physical process. So like temperature or current or heat. It's gonna give you a voltage related to that. That relationship or proportionality constant is known as the what? The proportionality constant that maps the physical process to the voltage has a name. I don't think it's on your slides, but not on this slide. What do we call that? Do you agree? It might look something like this. So if we want the mapping, some physical process, the sensor is going to take that physical process, convert it to a voltage that's proportional. Slope of that is this proportionality constant. Does that make sense? That's called the sensitivity. The slope of this is called sensitivity, or its calibration curve. We talked about 3 key attributes of analog to digital converters. Bits, number of bits that the analog to digital can convert with, how many kind of bins can it store a number in, sample rate, how fast is it sampling this physical process, and then the input voltage. How much voltage can the sensor in the data acquisition system sense? If you didn't have your sensor voltage, let's say your sensor outputted a voltage that was plus minus 5, and your voltage range was set to plus minus 10, what happened? What are you giving up if you do that? Does that make sense? Your sensor only goes to plus minus 5 voltage, plus minus 5 volts. Your data acquisition system is set up to receive plus minus 10 volts. Is that good or bad? Bad. Why is that bad? We're losing resolution by half. Yes. So if we match our sensor range and our input voltage, then we're maximizing the number of bins we can store that data in. Does that make sense, everybody? Okay. The resolution was defined by this, and if you kind of hopefully see that like if this was, we were changing this number and changing the resolution in that like verbal example we just gave. Yeah.
If you were out of range for like a physical sensor, what would happen to it?
You mean if your
like voltage was too high?
If you went outside the like calibration regime of the sensor.
Yeah, would it just like give you random values, or would it like break the sensor?
Usually it would like continue to work, become nonlinear, and then destroy the sensor. Yeah, usually they can go some amount overhead, but like eventually that will destroy the sensor. But it'll kind of like become nonlinear, usually. Okay, good. This is important stuff. This is about sampling. Here's our, if you see in gray, that's our analog signal. It's being sampled by that red line. What's the error? What's the error between the red and the gray called? What type of error?
Is that aliasing? Or is that?
No. Well, but aliasing is an important concept. Yeah. It's called quantization error. We're quantizing this gray signal, but we can't get its actual number. We can just get the bits that are closest to it. So depending on kind of like where the bit voltage falls within your data acquisition kind of bit range, it will kind of assign that. But that's why I look kind of stair-steppy, because you only have a certain number of bits to prescribe to that voltage. Aliasing would be this. Did I draw this last time? I have like a really nice version of this. you only sample so let's say your signal is actually the blue signal, because you're recording, that's what's the actual signal happening, but you're sampling it at the thick blue dots, and the red line goes through those thick blue dots. So if you sample the blue line too low of a frequency, what you'll reconstruct is the red line. You'll actually get points that look like a sine wave, it just looks like a sine wave of a lower frequency. That's aliasing. Nyquist criterion is really important. You guys know it. Then we talked about digital data acquisition instead of analog. All of your sensors are digital, which is nice. They're much more common. When I was like in grad school, they were like not common. But now the physical system and process is just, there's only one thing between the system and process and your computer, and that's the sensor. The sensor does all of the acquisition and sending everything for you. Nyquist frequency and sampling still applies, but you don't have to worry about the number of bits on your data acquisition card or anything like that. That is all set and defined by the sensor itself. Cool? Good? Then we started talking about sensing. We talked about specifically mostly the sensors that you're going to use. There's a gazillion types of sensors. They all kind of generally follow the same concept. They're gonna provide information on a physical process, and they're gonna have a data sheet that's gonna explain how that happens. For IMUs, we looked at kind of various types of IMUs and then accelerometer and gyroscope properties a little bit. Trying to think of a question I can ask you guys to kind of test your knowledge on this. What's the challenge? Why is this proprietary algorithm within the IMU, Cartesian acceleration and angular velocity are fused, and it outputs what and why? Like, why is it hard to get this?
Because you have to integrate over those terms, and especially if you have noise, it just accumulates a bunch of drift and like can cause like very inaccurate results very quickly.
That's right. So even if you have a signal that's really, really accurate, but not perfectly accurate, and you integrate that signal, it will become very inaccurate. So that's kind of what's happening here. So we use their internal digital motion processing engine, DMP, inside the NPU 6050. That's what gives us your ballbot's orientation. We don't have to worry about it. It's all done for us. So that's awesome. We talked about different types of encoders. This you definitely have to know. We learned encoders, a few types of encoders, and quadrature decoding. This is an optical encoder. I think you guys, this is what we use in our ballbot motors. Light is passed through a disk with slots. As the disk rotates, the light flashes on a photodiode or photodetector, and it determines like angular motion. Where does the system usually go? Like, where does this go in ours? These signals.
Or into the motor controller board with the Pico. It goes
Yeah,
into
they actually go into the Pico. And the Pico is counting them. It's counting all the pulses that go by, and it's tracking them when they change direction. And that's how we get information about psi. When that information is refreshed in your control program, that's where it came from. But these are very, very, very common. They're like pros are, they're high resolution, resistant to magnetic fields, low cost, relatively easy to use and robust, but they're complex. Sometimes they can be fragile, kind of depends on exactly how it's done. Ours are probably a little fragile on the flow loop motors. And then this I was kind of showing you, just like most of the time you'll see just A-B wires. But sometimes you see a not version of it, and that's for an additional layer of resolution applied. Magnetic encoders follow the magnetic field. This is an absolute encoder compared to a relative encoder like an optical encoder. Pros are high resolution, absolute, low cost, simple. I like these a lot. Quadrature decoding. How does this work? You have a question?
Yeah, I had a question. Sorry, it's a little bit up, but it was about the IMU actually.
Yeah.
You said that, or I saw like on the side, it can get angular acceleration, but can it can also get linear acceleration? Is that what it's saying? Like it's saying report x, y, and z acceleration and also x, y, z angular velocities. Sorry. Okay.
No worries.
I put the word linear in there in my head.
It's all good. Somebody tell me what is quadrature decoding and like why where did it come from? Like why does it exist and how does it work? Somebody we haven't heard from. Maybe sure, Omar, you can do it.
It tries to give you more of an absolute data for the encoders. So the smallest gap by the 1 lets you know how many spins it's done. So it tries to tell you a little bit more about that. Then the A and B are offset, so it can tell you which direction it's rotating in.
That's right. So we generally use, like if you didn't have 2 of these, if you only saw one of them, like something like this, you wouldn't know direction. So they're flipped, usually like offset by some phase, about 90 degrees, and then that's used to determine there's a logic that can compute direction. Essentially, it's no computation. So these are used, this is used widely.
What sensor is like keeping track of like if A or B is coming first?
A counter. So like these would go to a counter. So that would either be on a microprocessor, like what we're doing. So there's some pins that are interrupt routine pins that whenever they see a voltage change, they count a variable.
But how are A and B creating voltages, I guess?
Sorry, they what?
Like how do they create, like is that like a physical thing that it looks like, that it's like spinning or?
This?
Yeah.
Yeah, this is like what it can look like.
So how does that then become a voltage that gets sent to the counter?
This guy?
Yeah.
Because it passes light through a disk. That disk.
So it's also like kind of an optical encoder, but like
Quadrature decoding is really like once you have pulses, how do you understand the direction of those pulses? Those pulses can come from an optical encoder like this. It could also come from a Hall effect sensor. It could also come from a magnetic encoder if it were set up that way. But the quadrature part is set up to do any type of.
okay, so it could be present in some of the types of encoders we were just talking about.
Correct.
Okay.
Yeah. If you need to tell direction and all you have access to is pulses, you'll implement quadrature decoding. Yeah. So they tell you what direction, and then they have, some of them have index marks that tell you when it's made a complete rotation so that you know some sense of absolute motion. If you like, yeah, go ahead.
I guess I just had a question regarding the direction and like why necessarily like it's useful to know whether it's going counterclockwise or clockwise.
Why would it be useful to know that?
Yeah.
I don't think you could do a lot of like the robot tasks that you would need to do without knowing that. Like for example, you wouldn't be able to control the ballbot if you didn't know like what direction it was going. You could empirically determine that by like driving it with a voltage and kind of understanding what direction it's going. But yeah, almost always you need to know position, and you need that position to be able to tell you whether it's increasing or decreasing in motion. Yeah, sort of just a kind of a general requirement, I'd say. Something I was gonna say. Oh. Have you guys heard of a homing routine? Do you know what a homing routine is? Do you know what it is?
I think I like could be thinking of something completely different, but like returning it to like the base state, or like, for example, like a Roomba's homing routine could be going back to its charging station, like
Yeah, that's
inverting
probably-
all the motion it's done.
Yeah, that's probably a homing routine. That's not what I mean. A common thing that has happened in robots would be like turn it on, and then the first thing you do is move it through its range of motion. And so you're kind of showing it, here is your range of motion. It's going to take the signals and the encoders go from one side of range of motion to limit to the other. And then it usually knows, okay, like that's my range of motion. Then it can get an absolute information from it, from the encoder. Then it knows where it is. So like if you have a relative encoder, people can home the system, and that will tell you like absolute location. But that's just a side thing, you don't really need to know that. We talked about digital communication. This stuff you really need to know. I2C, SBI, USB, but we didn't really talk about that, but it's an example. Then we kind of talked about the mechanics of sending digital information. How does that work? What does it look like? How many wires are required? How is addressing done? What's the purpose of the clock line? It's not a trick question.
Make sure the data's coming in like live, like to be able to sync it,
Sync it how?
like when it's sent versus when it's receiving.
Close. How does it know? Do you know?
Well, does it give just a timestamp on the data so that if you like, I don't know.
Also close. It tells it when the bits are ending and starting. So like, you know, if you're looking at the data line, you may, if you had, it was all ones. So how would you know like how many bits were just transferred? You know, so like what the clock line does is it's separating the bits. Some communication protocols don't use a clock line. They just agree upon the speed of traffic, and then they don't have to send a clock line. Anybody know a type of communication that uses that? With no clock? SBI has a clock. Like RS-232. Something where you're like, you ever hear an old school modem? Be like that. That's an example. Okay, I2C. This was the general setup. Controller that's just talking to sensors, the I2C responders. I2C is addressed by what? Like, how do you know which chip is being talked to?
The address.
With its actual, as an actual address. I told you it was 8 bits, but I think it's actually 7 bits. Because the last bit is used, I think, to tell the system whether it's reading or writing. The purpose of that message is to read or to write. So I think it's a, plus if you guys ever do on your, if you ever do on your Raspberry Pi, if you do I2C detect -y, it's gonna print on the screen all the I2C addresses that are filled. And that little grid that comes up doesn't have a 250 slots. So I don't think it's 8 bits for that reason also. Cool. You guys should try that sometime. I2C detect. It's cool. What does this say? Like, what is the purpose of this section of the message?
Where in the chip that you're writing to, where in memory are you writing?
That is true. And what is that like? What does that do, or how is that helpful for us?
The chip that you're writing to, it has different functionalities based on where in memory something gets written to.
Yeah. So there's going to be, this is basically going to say like what functionality of the sensor are you using, and then this is going to be information associated with that functionality. Yeah.
So for the homework problem with the light, like is that then like when it asks for the address, it's referring to like, okay, like what type of functionality if it's like fading to whatever color, and then
That would be the opcode.
which is the second part, right?
Yeah.
And then the data would be like the specific values of RGB that you'd be like changing.
Except for it wouldn't be RGB, but yeah. That's correct, except for it wouldn't be RGB.
It was the other.
Yeah, so in that case, it's the use of the data payload changed when you changed the opcode.
I don't know, I was looking at the spec sheet for the thing and like the examples that were showing, I was just looking at RGB examples, so say it was like,
Yeah.
okay, whatever the like char was, or if it was like a C or something, and then it had like in brackets like the C and then comma like whatever the RGB values were. So I'm kind of confused, like how do you then like split those up into, would you just like put the C as the first thing in the code and then like the values would be in the data, or?
You mean like if you were actually structuring this message, how would you send it?
Yeah.
You would just package, like the low-level library would take care of things like start, write, knowledge, stop. Like it would sort of take care of those things. So you can just use an API that's like write I2C block data, and then you would give it the address, opcode and data payload, and it would package it and send it for you.
Okay. But if it's doing multiple things, like, cause I think the homework problem is asking for you to like create that address.
Yep.
Do you just like stack them, whatever like the
Yeah,
different
that
functions?
homework problem is just basically asking you to create these bytes. You don't really need to worry about the other tiny little bits, acknowledge and that kind of thing.
So for the homework, I think it was like you had to do like a rich teal color. I had originally just found the bits for like the H, the S, and the B of teal, which is like definitely more than 8 bits. Are you saying there's like one 8-bit?
No, okay, so you're saying like this is only 8 bits, but you guys have a payload that's 3 times that.
Yeah.
So that's just this communication protocol is flexible enough that I think it would permit that.
Okay.
So like I think you can keep adding the payload as long as the chip knows what to do with that information. I don't think it matters. That's my understanding, is that it wouldn't matter if this was 8 bits or 24 bits. Cool. This was kind of finishing I2C, talking about SPI. The main thing about SPI was what are its kind of the main points of SPI. There's a couple. Or SPI and how it compares to I2C.
There's like a specific extra chip select line that'll directly physically connect to the various responders rather than like you just specifying that in the message for like I2C.
So it uses the chip select line, one to each chip to flag it and say I'm talking to you. And then what's another comparison? Yeah.
Send data both ways.
You send data both ways, that's right. That required an extra data line. And then one other thing. How fast is it?
Slower.
Yeah, more than twice as fast as I2C. So I would say like pretty fast, 1 megabit per second. Not as fast as newer protocols, but for the kind of robots we're talking about here, that would be a lot of data. So if I were just choosing for speed, I would choose SPI. Is it true that the time on the communication bus, the time it is required to send messages to your various peripherals, is that an important amount of time or a not important amount of time? Is that significant or insignificant? What? It's actually significant. So, and I think I've mentioned, it's not in the slides, but I mentioned this off the cuff one time, but the time it takes to send messages on the bus can be a huge like driver of your system's loop timing. So this, in fact, it's the only thing that I've ever not been able to speed up. So the time it takes to communicate can actually be really long, and that can slow down your control loop. That can have negative effects on your row application. So if you care about timing, you might use something like SPI instead of I2C. And you can also, in your Raspberry Pi, you can increase the speed of the I2C beyond like it's 400 kilobits per second, which is like a little risky, but will work. Yeah.
Is the risk that you would be like losing data, or what's the risk of speeding up?
So risk would be like, it doesn't keep up and you lose data, or if it doesn't, data can get hung. So like it sort of stops and it's waiting for someone to do something, but they missed it, so the bus just waits, like stuff like that. Yeah, that's really actually really challenging, but it also can work fine. A lot of it depends on the length of your wires. Why does the length of the wires matter?
Farther for the data to go.
What?
Farther for it to go.
But why does that matter? Like, why is that a bad thing? What happens when the wires are too long?
More resistance.
More resistance, yeah. More capacitance is actually the issue. More capacitance, so it slows the rise of the kind of pulses. Okay, we're basically done. I just wanted to quickly tell you about OmniWheels. Ooh, it's close to ending. Let me just give you the quick OmniWheel overview, but these are really, really cool. They spin in 2 ways. They spin both around their axis and then also perpendicular to that axis. what's really neat about them is how we can direct motion. So if we have them in this tripod configuration, we can do holonomic motion of the robot. I mean, we can specify its position and orientation in any location. Where if we did that with 4 wheels, we wouldn't be able to do that. Same thing with cannon wheels. Cannon wheels, I think, are like more likely to be the kind of thing you see on the exam. So they're a little bit more straightforward, I think, on how they, a little more intuitive, I think, on how they work because of this 45-degree angle. And we did an example, I think, that talked about structuring these wheels, applying torque to move in a certain direction. Cool? Okay, this was the review. Hopefully it was helpful. I'll be in office hours, can talk to me. I'll start getting things ready for the exam, and I'll see you guys on Tuesday.